Energy of a horizontal simple harmonic motion system. In this lesson, we're going to look at the energy, mass, and velocity of a spring mass system. So here I have a spring drawn in green, and that spring is attached to a fixed point, something like a wall, and on the free end we have a mass attached to it. And right now the mass is located at what's called the equilibrium position of the spring. That means that there are no forces acting on the spring. It's not being pulled and it's not being compressed. Now any spring has a natural length, and at this length the spring force is equal to 0, and that's because there are no forces either pushing or pulling on the system. So a simple harmonic oscillator consists of a mass attached to the free end of a fixed spring. That's what we call it, a simple harmonic oscillator. Now if the spring is compressed or stretched a distance of x from the equilibrium point, the system will undergo simple harmonic motion. So there are three reference positions. The first one is when the spring is relaxed. When the spring is relaxed, there is no spring force, and the end of the spring is located at the equilibrium position. When the spring is stretched, that means we pull it, the mass is located at what we call x max, and the x is said to be greater than 0. It's a positive value. And you see that the x is in the positive direction and the force is acting in the negative direction. They oppose one another. Now if you compress the spring, so you apply a force from the outside in this direction, so you're moving the mass in the negative direction, negative x, the restoring force of the spring is going to try to push that mass back towards the equilibrium position. So at x max we have no velocity, and at x is equal to 0 we're going to have the maximum velocity, and we're going to further explore that. So the energy of a mass spring system, the total energy in the system, is just the combination of kinetic energy and the stored potential energy, or the spring potential energy. So the total energy of the mass spring system is equal to 1/2 mv squared plus 1/2 kx squared, and the velocity of that oscillation depends on x. So it depends on where the mass is located in its travels from the two extremes. Now the total energy, of course, is going to adhere to all conservation laws. So let's explore this position where the mass is located at a far positive extreme. So we're going to call that x max. Now x max is called the amplitude of the simple harmonic motion of the system. So that is the maximum that the mass is going to move away from the equilibrium point, and we call that x max the amplitude, and we give it a symbol of A. So x, in this case, x is equal to x max, and in this case, x is just equal to A. We're going to use that A right there. Now, the kinetic energy is equal to 0 because at x max, we have no velocity. That's the point where the mass is now as far as it can be. It's basically at v is equal to 0, and now it's going to return back towards the equilibrium point. Now, the spring potential energy is going to be equal to 1/2 ka squared because the x happens to have a value of A. So this applies when the mass is located at x max. So what we can do is we can take our energy formula and say that the total energy is going to be equal to 0 kinetic energy plus all of the spring potential energy, which is determined by the maximum value of x, or the amplitude. So that formula simplifies as total energy is equal to 1/2 kx squared, which tells us that the total energy of a mass spring system can be determined from the spring constant and what the amplitude is, the value of x max. And we see that the greater the initial stretch, or the greater the A, the greater the total energy in that mass spring system. And one last thing, at x max, the restoring force also happens to be the maximum value, and that's because the restoring force is equal to negative kx. So now let's have a look at the equilibrium point. What do we know at the equilibrium point? Well, at the equilibrium point, there is no restoring forces, and that's because we are at the equilibrium point. We have no stored energy because the spring is neither compressed nor stretched, and again, that's because we are at x is equal to 0. And the velocity is going to be maximum at that point. As this is moving back and forth, the maximum velocity occurs at the equilibrium point. And that's because at that point we have no spring energy. All the energy is kinetic. So the maximum kinetic energy occurs at the equilibrium point. Now, that's only going to be true if the system is moving. So if you have a mass spring system and you haven't done anything to it, then this last statement, of course, is not going to be true. So here's our diagram. We are at x is equal to 0. So our total energy is going to be equal to the kinetic energy using the maximum velocity, and we have no stored spring potential energy. So if we expand this formula, earlier we said that the total energy is equal to 1/2 Ka squared, and that's equal to the maximum kinetic energy of the system. And we've simplified, and we end up getting this formula to calculate what the maximum velocity is. And we see the maximum velocity depends on three things. It depends on the spring constant. It depends on how much you actually fully stretched it, or x max. And it also depends on the mass on the spring. So we can pull out the A there, and we get this final formula right there. So V max depends on those three variables. Now, what happens if we go the other direction? We compress this. Well, it's going to be similar to as if we stretched it. There's really no difference except the direction of the x. The x is going to be now in the negative direction, and the force is going to be pointing in the positive direction. So these two arrows right here, that's pretty much the difference between x max, which is positive, versus x max, which is negative. So stretching versus compression. And then we end up with the same formula. The only difference is that the A is going to be a negative value, but once you square it, it doesn't change anything anyway. Okay, so how about the mass at any position? So this is the exciting formula. What we have is we have the spring which is stretched, and the stretch is somewhere between the equilibrium point and the maximum value of x, or the amplitude. So we're going to set up the conservation of energy formula. The energy of the spring is a combination of kinetic and spring energy. And we know earlier that the total energy depends on the maximum stretch, or compression, A. So 1/2 Ka squared is equal to the kinetic energy and the spring potential energy. And we can take this formula and simplify it. So here's just kind of a general form. I don't want you to memorize any of these formulas. This is just the concept of conservation of energy, where the total energy, right here, 1/2 Ka squared, is equal to the kinetic energy plus the spring potential energy. And that formula will work for any position of x. Now, we can go a little further. We can say, well, what if we wanted to take this formula and incorporate the maximum velocity? What is the maximum velocity in this particular case? So we can take the formula, the Vmax formula from the previous part of the lesson, and rearrange it so it's a squared is equal to Vmax squared over k, and plug that into that formula, and we'll get a different formula. And that's what I want you to try. I want you to do that substitution and simplify, because that's good practice.